Can you hear me? Okay, can you hear me and can you see my slides? Awesome, great. This is my great pleasure and honor to be the introducer slash host for the today's speaker, Professor Saïda Guellati-Khélifa. So for during this tutorial, I'll give a little bit of introduction to quantum metrology, focusing on atom interferometry. So let's get started. So let's start from the very general concept. What is metrology? In short and in simplified terms, it is just physics of measuring many different physical quantities. These physical quantities can be really anything, like strengths of electromagnetic fields, or electrical thermal conductivity, some frequency shift to measure the timekeeping, or gravitational waves, or any fundamental constants. And maybe that's the most interesting one for today's purposes. Uh, Now, what is quantum metrology? Quantum metrology is just performing the metrology using quantum mechanical principles or quantum mechanical objects. For example, we use artificial atoms or just atoms and molecules and their spin degrees of freedom, or sometimes even the ensemble of those particles, in order to improve the quality of metrology. So, for example, can we improve the sensitivity of this metrological task using this quantum mechanical object? Or maybe not sensitivity, but maybe we can improve the bandwidth of sensing or the speed of measurement, or more pragmatically, like size of sensors, the weight or energy or cost, whatever. If there's any advantage using the quantum mechanical object, then it'll be the quantum metrology. So aside from this abstract concept, let's be a little bit more specific. How does quantum metrology work? So I brought out maybe the simplest possible examples built on the intuition of a qubit. So let's consider a quantum metrology of measuring a magnetic field. As we all know, the magnetic field can be measured using so-called a Ramsey spectroscopy. So let's simplify the situation here. Consider we have one fully controllable qubit that's coupled, qubit, which is a spin 1/2 particle, that's coupled to external magnetic field along z direction. And the strength of the magnetic field, B, is what we want to measure. And how do we perform the measurement? It's very simple. Step number one, we prepare the spin along some of the direction along the equator. So that's our initialization. And evolve the system under this this Hamiltonian. And then what happens is the spin will precess along the z-axis with the precession frequency proportional to the field of the magnetic field B. And after some evolution time, it'll rotate by an angle. But depending on the value of the B field, they'll rotate by different amount. Finally, we rotate these degrees of freedom in such a way that different rotation angle maps to the different population dynamics or populations by coherent spin manipulations. And finally, measure the polarization of the spins. And then what we get is this expectation value of the polarization will oscillate or change as a function of the B field strength. And by measuring the expectation value of the polarization, we can deduce the strength of the B field. And that's the main idea of how the quantum metrology work. Let's go a little bit more mathematical. So at the beginning, we basically prepare the superposition of 0 state and the 1 state. And over the time evolution, what happens is these two branches of the wave functions, the 0 state and the 1 state, picks up a different amount of phase. For each 0, you pick up a phase minus bt over 2. But if it's in the state 1, it picks up the phase like b times t over 2. Therefore, if you measure the relative phase between this 0 branch and the 1 branch, we can decode the information about the field that we want to detect. So essentially what we are doing is we transform the metrological signal B into the relative phase difference and measure the phase in order to deduce the value of the signal. So that's how it works. So let's take another example. So the example of measuring length, the physical length very precisely using so-called Mach-Zehnder interferometer. So this is a cartoon picture of the Mach-Zehnder interferometers. So it's very simple. We have a laser that illuminates light. And this light is split into two beams, two paths of beams using the beam splitter. On one path, it goes this direction, horizontal, and then reflected, and then reflected again to go into the detector. The other path is we go to the up, and then reflected, and then transmit it here to get to the two detectors. And then what we measure is laser intensity at one of the detectors. Like it just, the physics stays the same, but today we'll focus on this particular detector on the right here. So what happens is there's a two paths to reach this wave beam, and these two paths will interfere with one another. Let's say one of the paths has an optical, the light length, which is a light path L0, and the other one has a path length like L1. And what happens is if L0 is exactly equal to L1, or they differ by some integer multiples of the wavelength of the laser, those two pathways interfere constructively with one another so that your detector will detect a bright signal. However, if this length is slightly different one another or exactly equal to like odd integer multiples of half of lambda, they destructively interfere with one another, and then you will detect a relatively dark signal. Therefore, if you plot the signal strength of the detector as a function of length difference between L0 and 1, and you will have oscillating signals where this oscillation has a period that's set by the wavelength lambda. And that way we can precisely measure the length difference between L0 and L1. So let's again go to the mathematical descriptions. So intensity of the light at the position of this detector is the linear combination of the intensity coming from two branch. So we have a two term, like zero branch and one branch. The zero branch picks up a phase, which is omega times t, where the time is basically the length of the path divided by the speed of light. Then the same way, we have omega times the time, where the time is the length divided by t. So essentially, the relative phase phi between these two branches is given by the distance difference divided by lambda. And that's how we measure, and then how the interference works to detect the length scale. So we talked about this simplified example, but however, this is actually what's being used in the real world applications. And maybe the most famous example would be the LIGO. So the LIGO actually utilizes this interferometer. The geometry looks slightly different. They use a Michelson interferometer rather than a Mach-Genta interferometer, but the working principle stays exactly the same. And what they measure is if there's a gravitational wave, one of the length of one of the arm changes slightly relative to the other, and we are detecting the signal by the interference of the light. So this is a true, even though the principle is very simple, this becomes very, very powerful. So the natural question to ask is then, okay, then how precise can we measure using these kind of interferometers? And the answer is simple. In general, the sensitivity is determined by how sensitively the phase changes as a function of our signal that we want to detect. For example, for the case of the Ramsey spectroscopy, we show that this phase is a function of B field and we have oscillations. And for our Mach-Genta interferometer, we show that as a function of length difference, we measure this fringe. And they're this oscillating with the period lambda. And these interference patterns, or this oscillation, essentially act as our ruler. So as we know, if you want to measure some quantity, it's better to have a fine ruler because we can read off the better precisions. In other words, the precision is essentially set by how rapidly those fringes are oscillating as a function of the tuning parameters or the signal that we want to detect. So let's do the sensitivity analysis. For the example of Ramsey spectroscopy, the phase we accumulate is given by the magnetic field strength times the coherence time that we use to accumulate the signal. Therefore, assuming that we can measure this phase up to a certain finite precision, the minimum strength of the B is inversely proportional to our coherence time or the evolution time. Therefore, achieving a longer coherence time gives us a better sensitivity in B. How about the interferometers? Like in this case, the phase difference is set by the length difference divided by lambda. Therefore, given our same sensitivity for phi, the shorter the wavelengths, we get the better sensitive. We can resolve the shorter distance difference. So it's important to use a short wavelength lambda. Therefore, if you want to improve the sensitivity for the interferometer, then what's very natural to have is choosing an object, choosing a say light field that has a very short wavelength. And that's the idea behind using the matter wave. So in 1924, the Louis de Broglie actually made a conjecture that not only the light, actually the matter, like the atoms or molecules, when they have a finite momentum, they can be described by a wave. They exhibit a wave-like behavior because of quantum mechanical principle. Specifically, the wavelength lambda is determined by the Planck constant divided by the momentum. And if you have a massive particle with a certain velocity, and this lambda can be very small. For example, in today's talk, we'll mostly talk about the rubidium atoms that has a mass 1.4 times 10 to the negative 25 kilograms, which sounds very small, but if you have a little bit of velocity, say 6 millimeter per second, and that amounts to the de Broglie wavelengths, which is 780 nanometer, which is comparable to the wavelengths of the optical light. That means we can use atoms to do the interferometer just like we do with the laser light. Except that now that we are using atoms, there are a few advantages. First, if you increase the velocity, your wavelengths will become shorter, so we can achieve high sensitivity. At the same time, this phase accumulations is not only about the length, but also about anything that affects the energy of those particles. For example, the gravitational force, or generically kinetic energy, or the momentum change of the particles, or even the fundamental constant that's associated with this particle. So that is the idea behind why the matter wave could be useful to use for the metrology. But there's a challenge. Suppose we can implement the Mach-Zehnder interferometer using atoms. Previously, you had a beam splitter, but it's not clear how to put the beam splitter for the particles. And the idea is we can use a laser pulse in order to implement this effective beam splitter. So let's see how it works. Consider we have an x-axis of time and the y-axis is the position of atoms, and consider the atom that's moving with the momentum p. And each atom has an internal state like 0 or 1. Let's assume all the atom is prepared in the 0 state at the beginning. And they are propagating over time because they have a finite momentum. But at some point, we apply a laser pulse, like pi/2 pulse. And then what happens is after the pulse, this atom becomes in a superposition state, where the state is given by linear combination of nothing happened, so still in the 0 state with the same momentum, or the atom observes one quanta of light and becomes in the excited state 1 and also it has a momentum kick transfer from the photon, so that your new momentum is plus like h bar times k. The k is a momentum wavelength, the wave number. And then consider another pi pulse, where in the upper branch we have stimulated emissions, and the lower branch we have the resonant absorptions, resonant excitations. And then they accordingly also exchange their momentum behavior. And finally, we apply pi/2 pulse again, such a way that these two branches can interfere one another. So there's a one-to-one like correspondence between the interferometer and this pulse sequence, where this upper branch is associated with the upper branch of the interferometers, and the lower branch is associated with the lower branch of the interferometers. Finally, we can measure the population difference between the 0 state and 1 state in order to measure the relative phase between these two branches. So this relative phase can be also computed quite easily. So let's consider the upper branch. For the upper branch, your total accumulated phase times h bar is given by the first evolution, so energy of the excited state, plus the kinetic energy of the particle multiplied by time, total evolution time t. And for the second half of the evolutions, we accumulate the energy of the 0 state plus the kinetic energy of that of the momentum p times time. We can also consider the phase accumulating the lower branch, where at the first half we stay in the ground state, a 0 state, and then momentum p. The second branch is in the excited state with the momentum p plus h plus bar plus times k. So in these particular configurations, these two branches experience exactly the same phase because they accumulate the phase in the opposite order, but they spend the same time during the ground state and the 0 state and the 1 state with the two different momentums equally. So this is well balanced. However, the situation becomes different if you turn on the gravity field. For example, in the upper path, suppose this position is along the z directions. So upper pass, we move to the up direction further and then spend time there. In the lower branch, we do not move to up directions or relatively less and then move up direction later. Therefore, their position degrees of freedom is separated for the two branch, and because of the different positions, they accumulate phase for the different gravitational potential field. In that way, the total phase difference between the two branch is given by the gravitational accelerations times the momentum k, wave number k times the evolution time t squared. And by measuring the phase difference between these two paths, we can essentially measure the gravitational potential energy. And we can be more creative. So there's another sequence where we do not consider the pi pulse in the middle, but split into 2 pi over 2 pulses. Otherwise, it looks very similar. And this particular interferometer is called the Ramsey-Bourdais interferometer. And I can walk you through like how it works. So again, we start from the atoms in the zero state with the momentum p. After first pi over 2 pulse, we have a 2 branch in superpositions. After second pi over 2 pulse, we have a 4 branch because each branch like cancel out. And after third pi over 2, we have an 8 branch. And finally, we have a pi over 2 pulse, but we can arrange this pulse sequence such a way that only the 2 branch out of the total 8 interfere one another, leading to our particular measurement outcome, like interference. And we can talk about the phase difference of these 2 particular branch. Repeating the same calculations, we again check that naively those 2 paths accumulate exactly the same phase. So like they will constructively interfere. However, we can consider applying extra operations such as applying an additional momentum kick in the middle. And similar to the gravitational field, if you have an extra momentum kick in the middle, total accumulated phase will be affected. Because of the momentum kick, we will change the different kinetic energy so that the net phase difference between the 2 branch will be proportional to the change in the velocity times the wave number times the total evolution, the coherence time t. In this way, we can also measure the momentum kick delta V by this using the Ramsey-Bourdais interferometers. So I hope that I could convince you that using the atom interferometers, we can measure various kind of quantities such as the gravitational acceleration constant, or this momentum kick, or their associated fundamental constants of physics. So with that, let me finish my introductions, and the real main part of today's talk will be done by Professor Saïda Guellati-Khélifa. And she made a lot of like important contributions to using ultra-cold atoms to perform high precision measurement. In particular, I believe that she will be talking about how to precisely measure the fine structure constant using atom interferometers and talk about its implications to the standard models. And with that, I'd like to welcome Saïda for her talk.
Thank you, Sonun. Okay, I will just share my slide so I can just open it. Okay. First, I want to thank Dan and the organizer to give me the opportunity to be here with you today. It's really a great pleasure to present our work in Paris. Second, apologize for my bad English. I will speak my spoken English. I will speak slowly, and if you have any question, any problem, you can stop me. No problem. So. Today, I want in this talk, I want to answer two questions. The first one is how accurate determination of the fine structure constant contribute to the test of the standard model. The second one is how we determine the fine structure constant using quantum velocity sensor. And in the third part of my talk, I will discuss some research direction toward the next generation of quantum sensor based on atom interferometry. So first, what the fine structure constant is a dimensionless constant given here, where E is electrical charge, H bar, C is the speed of the light, epsilon is the permittivity of the vacuum. This constant is equal 1 divided by 137, has been first introduced by Sommerfeld to explain the splitting of Balmer line in hydrogen. In fact, Sommerfeld proposed a naive model where we consider elliptic trajectory for the electron, and let me say, introduce the relativity by Hans to explain the spectra of hydrogen atoms, and which is extra remarkable that the formula obtained by this naive model, which not take into account the spin of an electron, was exactly the same than the one derived from Dirac equation. And in this Dirac equation, describe perfectly this, the energy level of hydrogen, sorry, and he give for the first time the relationship between Rydberg constant and the fine structure constant. And this formula is a key point of our experimental approach. Also, the Dirac equation, the second term corresponds to the spin orbit that explain perfectly this hydrogen spectra. So we use this formula, which correspond give the relationship between the ionization energy of the hydrogen and the kinetic energy of the electron in first Bohr. And from this formula, we derive the relationship, the expression of the fine structure constant as a function of the ratio H Planck constant divided by the electron mass. But as is hard to determine electron mass, we introduce the relative mass of the relative atomic mass and the electron atomic mass. And in this case, we can express this formula as function of the ratio H over M, where M is atomic mass, and in our case, rubidium mass. In this formula, all the terms are determined, measured by accurately. For example, the Rydberg constant is known with uncertainty of 210 to the minus 12. Relative rubidium relative mass, defined as atomic mass divided by unit mass, is determined at 710 to the minus 11, and all by measuring cyclotron frequencies of charged rubidium. Also, the electron mass, relative electron mass, is also measured with high accuracy. And today, the accuracy, precision on the fine structure constant alpha is limited by this ratio H over M between the Planck constant and atomic mass. So, and this ratio appear in this recoil velocity. You know, when atom absorb a photon, it move back because he take the photon momenta, and the recoil velocity equal to h bar k, where k is the wave vector, and m is the atomic mass. And the goal of we can deduce the ratio h over m from the measurement of this recoil velocity. to have to give some order of magnitude, this recoil velocity is too small. For example, for rubidium atom equals 6 millimeter per second. So only two groups on the work are working on this kind of experiment. The group of Holger Müller, in group who Holger used a cesium atom, and our group in Paris. So now, why is it important to measure precisely the fine structure constant? In fact, the fine structure constant is a coupling constant of electromagnetic interaction. And then it appears in many fields of physics. For example, we can deduce this constant by measuring the muonium ground state hyperfine splitting, in other terms, by doing spectroscopy of the muon. One can determine this constant by measuring the Van Clebesing constant, which is a constant of quantum Hall effect. And you see that the fine structure, the Van Clebesing constant is equal to the vacuum impedance divided by the fine structure constant. It could be deduced also by comparing the anomalies magnetic, the experimental value of the anomalies magnetic moment of the electron to its value predicted by the standard model. And as we say in this diagram, I show the improvement on relative uncertainty on alpha over the last years, and you see that since 20 years, the most accurate value comes from the recoil measurement and the anomaly magnetic moment of the electron. And we improve by 1 order of magnitude the accuracy every 12 years. In fact, the interest to measure precisely alpha from different way of physics leads to test the coherence of the, to test the validity of different theory. But in our case precisely, we want to, the goal here is not exactly to deduce alpha from different experiment, but the goal here is to use, as I will show later, the independent value of alpha to determine a prediction, a theoretical value of a electron moment anomaly in order to test if there are new physics beyond the standard model. In fact, if there are difference between the prediction and the theory of these of the anomalous magnetic moment of the electron, this could be a signature of new physics beyond the standard model. But up to now, I don't define this quantity, and I want to say a few words about that. This the electron magnetic moment of the electron is defined here, and the Dirac equation predict that the G factor of the electron equal exactly 2. But measurement done by quotient Foley with the gallium, indium, and the sodium in 47 show that this G factor is slightly different from 2. And this difference, in fact, is due to the fact, to the coupling of the electron with the vacuum fluctuation and the effect, sorry, of the vacuum fluctuation of the polarization of the and polarization that modify the electron, the magnetic moment of the electron. And the first, and what we call anomalous magnetic moment of the electron is this correction, which is mainly due this effect. In fact, the quantum vacuum is like the sea, where a pair of particle and antiparticle are created and annihilate in short time, and these modify the charge of the electron, and then these modify the magnetic moment of the electron. And the first calculation was made by Schwinger, and it is exactly equal to 1/2 alpha fine structure constant divided by P, and is correspond to this diagram, Feynman diagram, when electron emit a photon before interacting with a magnetic field, and then absorb this photon to conserve his energy. And this first correction is contribute to the large contribution to this correction. But we can go to higher order, and as alpha is coupling constant of electromagnetic interaction, and then the value of alpha is too small, one can consider this higher order correction as a power theory of perturbative theory of alpha. We see here that there are two parts of two kind of coefficient. Some coefficient are independent of mass, and the second one are depend on the mass, and their consider the contribution due to the creation or annihilation of electron and positron, muon or anti-muon, and so that. And these, the predicted value of electron moment anomaly include also a contribution of hadronic and weak interactions. All these parameters are calculated. I am sorry to show you this hard slide, but the idea here to show you that the calculations are really hard. For example, for the fifth order, we need 12, more than 12 Feynman diagram. But these calculated are made only by two groups in the world, and but they are really precise. We show here the precision on the predicted value of electron moment anomaly is now limited by the value of the fine structure constant, and the contribution to QD. I mean what I mean by the contribution of QD is the uncertainty on the evaluation of this term, this coefficient who are evaluated up to the 5 order in alpha. And currently, in the theoretical point of view, the limitation come from the hadronic contribution, but is close to the QD evaluation. Anywhere, we have more than 1 order of magnitude in terms of uncertainty on due to the uncertainty on the fine structure constant. So, and in what about the measurement of this anomaly? In fact, this anomaly is measured following the scheme proposed by Demelt, and the idea is to measure directly the anomaly frequency, which is the difference frequency between the spin frequency and the cyclotron frequency. Okay, in fact, we measure these by using electron in pinning trap and in presence of a magnetic field. And we, in this case, as you know, the electron presses around the magnetic field, and also we have and the G factor equal to the spin frequency divided by cyclotron frequency. And when we show the energy level of the electron, we can measure directly this anomal frequency, and also we can measure this cyclotron frequency. And these measurements are done by frequency jump spectroscopy in the group of Gabriel-C at Harvard. And this group are able to measure this quantity directly with uncertainty of 0.28 part per trillion. In fact, the advantage of this method that the difference is about 10 to the minus 3. And if we are able to measure the frequency at 10 to minus 10, which is easy, we can deduce G factor with uncertainty of 10 minus 30. And currently, the group of Gabriel-C are building a new experimental setup where he planned to better control of systematic effect that limits this measurement, like electron motion and also the gradient, magnetic field gradient. They also plan to measure simultaneously these two frequencies, and they expect one order of magnetic improvement on the measurement of this quantity. And now, why is timely to improve this comparison between the prediction and the experimental value of this anomaly? This has been recently highlighted by a recent measurement done by Fermilab by Miriam G-2 collaboration. Since a few years, many years, there are a great important discrepancy between the theoretical and experimental value of the Mayan anomaly. And this discrepancy has been of about 4 sigma, has been recently confirmed by this new measurement. And the question is, this discrepancy is due or not to new physics. And if this effect is due to new physics, that means the contribution of a dark particle that has not considered in the standard model, it should be observed also on the electron. And as the Mayan, the electron is heavier, the ratio between the electron mass and Mayan is about the mass of the electron is of the Mayan is 200 larger than the mass of the electron. This effect, using a naive scaling, this effect could be smaller on the electron. And if we consider this discrepancy, this effect could be about 6×10 to the minus 14 on the electron. And in this diagram, I show the contribution to the delta AE. Delta AE is the difference between the experiments and the theory, and the uncertainty of the experimental measurement, and also of the different terms that contribute to the theoretical value of a electron moment anomaly. And we see that now we still the main contribution come from the value of alpha, and I mean from the measurement of this ratio H/m. And in the following, I will just show you how we obtain this measurement. but we are close, and I think we can, by improving by factor 0.8, we will be lower than this green line, which correspond to required uncertainty to observe this the Mayan effect on the electron. As in parallel, group of ARVA expect to improve this the uncertainty on IA by 1 order of magnitude. We hope in the few next year try to explain the discrepancy on the Mayan sector. Now, how we determine the fine structure constant using quantum velocity sensor. So in fact, we need to use a Raman transition, because in simple scheme, when atom absorb and emit spontaneously one photon, the recoil is not well defined. To measure the recoil, the K idea is to use a Raman transition, because in this K atom case, atom absorb a photon from one wave and emit a stimulated photon in the second wave. And in this case, he get exactly 2h per k divided by m, 2 recoil velocity, and we control perfectly the recoil velocity by controlling the laser beam. And the principle of our experiment is the following. First, we need 2 ingredients. The first one, a quantum sensor, that means atomic interferometer based on Raman transition with a sensitivity sigma V. Sigma V is the sensitivity of our quantum sensor. But we need also a technique to transfer to the atom a large number of photon momentum. In this case, we can improve the sensitivity on the recoil measurement is given by the sensitivity of the velocity sensor divided by the number of photon momenta transferred to the atom. And to transfer this number of atoms, we use a powerful technique which called Bloch oscillation technique, what I try to explain in this slide. The idea here consists, the principle of this technique consists in shining the atom by a moving standing wave. It obtained by shining by 2 laser counter-propagating laser beam with close frequency, but we sweep the frequency difference between the beam. We sweep the frequency difference between these 2 laser beams. And in this configuration, atoms, because the light shift, experiment a periodic potential, but moving periodic potential. When V0 sinus square k is the k vector, x minus x0, and x0 is the position of nodes or maximum or minimum of this the potential. Now, if we consider the accelerated frame, okay, of this wave, in this accelerated frame, atom experiment periodic potential plus inertial force. Okay. And in this periodic potential, like in solid state physics, the energy level of the atoms are in a band structure like that. Okay. And then when we apply this force, atom initially prepared in fundamental bound move in this fundamental bond. And if we choose the acceleration in such way that we respect the adiabatic criteria. That means that we avoid the transition in this critical area. And in this case, if we respect this adiabatic area, atom still in the fundamental bond, and they experiment a periodic structure. And this periodic structure will be printed on their dynamic, okay? That means that the motion of the atom will be periodic in the accelerated frame. Also, what we see, the momenta of the atom will be also periodic. This has been observed for the first time by group of Christophe Salomon at Paris, and in the same time group of Ryzen, I think, in Austin, and they observe, you see here, the oscillation. Here is number of atoms as a function of atomic momenta, and you see a periodic behavior here of with period 2b equal to h bar k divided by the acceleration here, I mean beta, beta. They observe this behavior, and then we show also that the mean velocity of the atom evolves periodically with the same period. But if we come back to the laboratory frame, we can show that after n Bloch oscillation, atom increase this momenta by 2n h bar k. And this means that we can transfer to the atom in the laboratory frame n h bar k depending of the number of oscillation that we can choose. It depends on the ramp, total ramp of the laser frequency. This process is very efficient. In our experiment here, I will show you the efficiency as a function of 2b, the Bloch oscillation period. And if we are in this area where we respect the adiabatic criteria in order to avoid the loss to the upper band, we can obtain efficiency close to 1. In our experiment, we are able to transfer 1,000 photon momenta in 6 milliseconds with efficiency of about 99.99, close to 1 per record. This technique allows also to control precisely the velocity and the position of the atoms, and as I will show, we use it to perform what we call our atomic elevator. So now I will discuss the second part, second ingredient, as shown by Sonwoon. The principle of atom interferometry consists by using a light pulse to create a coherent superposition and to mix these two atomic wave packets and to measure the probability to find atom in one state or fundamental or excited state. And this probability depends on the phase shift accumulated during the interferometric sequence. And for atoms, as atoms are sensitive to force, this phase shift by measuring by atom interferometry can be used to measure velocity, acceleration, or forces. And the question is how we perform this beam splitter in this in our experiment. For that we use the basic ingredient, the scheme that proposed by Steve Shu and Kazevich 19, and the idea consists on using Raman transition between the hyperfine level of fundamental state. The idea consists by shining the two atomic wave, the atom by two counterpropagating wave. Okay, and in this case, in the case where we are from detoning in order to avoid spontaneous emission, and one can show that starting from atom in this state with momentum P, we can create a current superposition between this state and this state. And this, as writing the momentum conservation, we can show that this state, the external degree of freedom between the two wave packets differ by h bar k effective, and k effective is the difference wave vector between this wave and this one wave. In this formula, which is important, that we see that atoms that perform the transition, the phase of the laser are printed on the wave packet that perform the Raman transition. And also there another term, which is energy term, which corresponds to the free evolution, the phase accumulated in free evolution of the wave packet, and it depends of the energy of the atom, which include the internal energy and also the kinetic energy of the atom. By choosing the effective Rabi frequency times the interaction time equal P/2, we can show that we create a coherent superposition between the two. Voila, this is exactly equivalent to 50-50 beam splitter in optics. And I just a last point, and this in this configuration, these transitions are velocity sensitive, and then we can select a velocity class by doing this transition. That means this transition is also selective in velocity, and the width of selected velocity depend on the duration of the light pulse. So, and here as shown by before, this is the scheme of the configuration of Ramsey-Bordet atom interferometer. It consists in two pairs of P/2 pulse, and the probability to find atom, for example, in the case of the rubidium in F equal 2 or 1, it depends on, is given by this formula for the case of F equal 2. And here you have atomic phase and the phase of the laser. In the atomic phase is the phase difference accumulated between the two paths, and is mainly due to the free propagation, and the phase shift due to the laser is the phase printed by the light at each P/2 pulse. And as shown before, if we apply between the two pairs of pulse delta V change of velocity equal to and Bloch recoil velocity, one can show that the atomic phase equal exactly as shown by Sun just before. The atomic phase shift equal T Ramsey times K Raman, which correspond to K effective times delta V, the change in velocity in between. And we can write this formula by considering delta Z, which is the separation between the two arms of the interferometer, which equal H bar K M, which recall velocity, which is the velocity difference between the two wave packet, times T-ram C, and we show that the sensitivity to delta V equal to the separation between the two arms of the interferometer times the atomic mass divided by H bar. In our case, delta Z is close to 215 micrometer, which correspond to phase sensitivity of 3 micrometer second minus 1 radian per radian. And in practice, what we do, if the phase due to the laser here is equal to the frequency 2 pi times the frequency difference between the Raman beam between the second pair of P/2 and the first one. And the total phase shift equal to this formula. Now, how I will show you the experimental setup. Our experimental setup is here. We produce about 10.8 rubidium atoms at 4 microkelvin with in the sphere of radius 6 micrometer. And the key point here is to control the interferometer sequence take place in this tube, where we control perfectly the magnetic field. Here I show you the magnetic field is controlled better than 15 nanotesla. And the second key point, as the phase of the difference phase between the two lasers are printed on the atom, the case point is to control perfectly the phase difference between the two lasers. And for that, we use this scheme. We send the two Raman beam in the same fiber, and then with orthogonal polarization, we have a beam polarization beam splitter here, and then the two laser beam, Raman beam arrive in this direction. The cube reject one, and the second one is retro-reflected. And in this configuration, we have two counter-propagating laser beam. The mirror, retro-reflected mirror, is supported by a passive isolation platform. And here we have a complex frequency chain that lead to phase lock the two lasers and to scan also the frequency of the laser during the interferometer in order to compensate the Doppler shift during the free fall of the atoms. Also, this chain will allow to scan the frequency of the laser between the first and the second pair. Also, these two lasers are phase locked, but in this, the frequency of one laser are stabilized in ultra-stable cavity, stabilized in atomic reference, and we measure the frequency of this laser by using a frequency comp, which is referenced to atomic clock, cesium atomic clock. So this is the sketch of the experiment as mentioned here. We start products here. Atoms are moved to this interferon tube. Here I show you the trajectory of atoms. We use what we call atomic elevator. It consists in two Bloch pulse. The first one transfer about 600 recoil to the atoms in order to launch them in vertical direction. And the second one is the stop atom here at a given position. It depends on the number of recoil that we transfer in this side. And then after atom move, we apply the interferometer sequence. We see here the two pair of P/2, this one and this one. And in the center, we have the Bloch beam for the coherent acceleration. And finally, we detect atom in this area. And in between, we select a narrow velocity class because we launch all the atom, and just before to stop the atom here, we select narrow velocity class before to start the interferometer sequence. And finally, by using two light sheets, we measure atom in f=1 and f=2, and from this measurement we deduce the probability, the fraction of atom in f=2. Here I show you a typical fringes. These each point are obtained by using all the sequence. We produce atoms, launch them, and so that. And we repeat this sequence by changing the frequency of the Raman beams during the second pair of the pulse. Okay, here we have this parameter. We record 50 points in 1 minute. And by fitting these fringes, we find the frequency of the center, which corresponds to this phase shift = 0. And from this frequency, we deduce this term. We are able to determine the center of the fringes with uncertainty of 0.047 Hertz, which correspond to a sensitivity in terms of velocity of 20 nanometer per second, which correspond to a sensitivity to h/m to 3 × 10⁻⁹. We detect about 10⁵ atoms, and we are 2 times our standard quantum limit. We are not limited by standard quantum limit, we are still limited by the vibration. In this simple scheme, I don't consider the gravity and also the level shift, like light shift or essentially light shift. And but if we can get rid of these two effects by choosing a suitable measurement protocol. In fact, we to deduce value of h/m, we consider 4 spectra. If we look at this formula, if we have the direction of the acceleration, that means in which direction we transfer the recoil, in the upper or in the downward direction. And by changing the direction of the acceleration, that means that epsilon b take value plus or minus 1, we can get rid of the gravity. We do measure two spectra by just changing this direction of the acceleration, and then we can cancel the gravity. Also, by changing the direction of the Raman beam, this is simply done by inserting here lambda over 2 here in order to change the polarization of the retroreflected beam. One can cancel here the contribution of constant level shift. And the value of alpha is then deduced from these 4 spectra. The value of H over M is deduced from these 4 spectra. So here I show you our data. We have a really stable and reliable setup, and we can get the measurement all time. Okay, for example, this set of data has been done during all the weekend. We have a good statistic. We see that the Allen variance scale as square t, and we have a sensitivity of 4.3 10 to the minus 11 on alpha on 48 hours. Thanks to this high statistic, we was able to do measurement by changing the experimental parameter like duration of block period, number of recoil, or duration of TRMC in order to check the coherence of our data. Here is our error budget. As usual in atom interferometry, we are limited by the wavefront curvature and wavefront distortion, and in general we are limited by the profile of laser beam. Why? Because up to now I consider a naive model of and the perfect model of plane wave. I consider that the k vector equal mu divided frequency divided by the speed of the light. But unfortunately, in the true life, we have a Gaussian beam. And then in this case, we need the effective wave vector equal to the gradient of the phase of the laser beam. And in the case of, we need to add a correction due to the fact that we are far from this model of the plane wave. In the case of the Gaussian beam, we can calculate perfectly this correction using the usual formula of a Gaussian beam, and we see that this correction scale as 1 divided by the waist of the laser, and also you have another term which due to the curvature of the wavefront. Larger is the laser beam, the waist of the laser, smaller is this correction. But in other side, we need to, when we use a larger beam, we need to use higher power. In fact, this correction is in fact due to the dispersion of the wave vector, which correspond here to the divergence of this beam. And this effect is the main contribution to our error budget, main contribution of our error budget also. We also discovered recently a new systematic effect, which which depend on the efficiency of Bloch oscillation. By changing the efficiency, we see that the value of the recoil, measured recoil, change up to 10 to the minus 7. And we spent a lot of time to understand the origin of this effect. And this, in fact, due to the short scale fluctuation of the intensity profile of the laser, and this effect has been calculated by just considering we calculate this correction by using a simple formula in paraxial approximation, and we show that this correction depend on the Laplacian of the amplitude of the electric field, or in other terms, it depends on the Laplacian of the intensity. And as the probability or the efficiency of Bloch oscillation depend also on the intensity, there are a correlation between this correction and the probability to perform a Bloch oscillation. And that means that, for example, if we are here and we are at the limit of Landau-Zener losses, one can lose atom in this position, and atom in this position are accelerated, and these modify strongly the total recoil observed, total recoil that we measure. To overcome this effect, we propagate the beam to smooth the profile of the laser, and then we take care to work at efficiency close to 1. And in this case, we reduce the contribution uncertainty on this effect to about 210⁻11. So here our new value, okay? And in this diagram, I present the most accurate determination of the fine structure constant, in particular the one that come from the measurement of the cesium recoil. And here is our new value. We achieve a relative uncertainty of 8×10⁻11 with very good statistic, but unfortunately we have a large discrepancy with the value from the cesium measurement. There are a discrepancy of 5.4 sigma with the measurement of our colleague Holger Müller. So this value improves the test of QD calculation, but the difference between the experiment of the theory, since it's still limited, dominated by experimental value of electron moment anomaly, the sign of difference is different, which means that the contribution, the nature of hypothetical dark particle that could explain this difference could be different. Can discuss this point together later. So our result reject with 95% confidence level delta AE in this region, and by using a formula that link the delta AE to the parameter that are the mass and the coupling of hypothetical particle that could induce this difference between theory and experiment, one can plot, one can reject, one can set a limit on this theory. And our new value here, in particular, favored the hypothetical Higgs boson that could explain the anomalous excess of electron-positron pair observed recently in the decay of the excited beryllium nuclei. And our measurement favored this region. So another interest of this new measurement is in the context of new international system of unit. As you know, the new system proclaimed in May 2019 they are only based on fundamental constant. In particular, the atomic mass, the mass, the new kilogram is now defined by fixing the Planck constant, and then our measurement lead directly to the measurement of the absolute measurement of the atomic mass. Also, in the new assay, the Avogadro constant is also fixed, and the molar mass of the carbon will not longer be exactly defined. And our new value give the most accurate value of the molar mass, as well of the mu0 epsilon, the vacuum permeability, which is now has not a fixed value in the new assay. And in more general, this new value improve the uncertainty of 90 fundamental constant listed by the CODATA. So now I finish my last part of my talk to discuss few direction for the next toward the next generation of quantum sensor based on atom interferometry. As if you remember, in my title, I add quantum sensor version 1.0. In fact, our experiment is based on the simplest concept of atom interferometry. We use Raman transition, we use thermal atoms, not ultra-cold atoms, and these show the potential of quantum sensor based on atom interferometry. And nowadays, there are a lot of projects in the world aiming different kind of measurement or test, for example, measurement of Newtonian constant, testing of force at short range, or testing the principle of equivalence. And all these projects aim to achieve very advanced tests. I don't have time to comment all the many experiments. I just choose to comment two experiments. The one that aim to test the quantum mechanics and gravitation, mainly the equivalence principle. The idea is to launch two atomic spaces different and to measure the gravity of these simultaneously on these two spaces, and to deduce what we call the Edvos parameter equal GA minus GB, where GA and GB are the gravity or acceleration measured for with the two space A and space B. And there are three main projects in the world. The project of Mark Kazivich at Stanford was use a tower of about 10 meters, another in Hanover, and another new project in China. And recently, Mark Kazivich achieved a sensitivity of 10 to minus 11 by racine de Hertz, and show and determine this this parameter with a relative uncertainty show this parameter, determine this parameter at 10 to the minus 12 using free fall of rubidium 8785 during 2 seconds. And the target of this experiment is to achieve, to improve this sensitivity by 4 orders of magnitude. Another ambitious project.
Yeah. We are almost on time, so maybe
just
good to wrap up. Yeah.
Okay, I just yes. Okay, I just conclude. There are another project on the European that aim to detect gravitational wave using atom interferometry. There are 2 main projects, the European project and another project in USA. And the interest is to, the atom interferometry is sensitive to a frequency range with not attainable by using LIGO or Einstein telescope, etc., are sensitive to this spectral range. And of course, to achieve this, the performance requirement for this project is really hard. For example, ultra cold atomic source with and also I don't have time to explain how it works, sorry. And also we need to use to improve the sensitivity of the interferometer by many order of magnitude, at least 5 order of magnitude. There are 3 research directions: development of ultra cold atoms, mainly high density, ultra low temperature in short cycle time. The second research axis is to use large momentum beam splitter. The idea is instead to split the 2-wave packet by H-bar K effective, we split this by mini recoil. And in this case, some encouraging result has been obtained in group of Stanford and also in group of Berkeley. But these large momentum beam splitters are still susceptible to dephasing from wavefront perturbation and laser intensity inhomogeneity, and the contrast at high order of diffraction still smaller. And the last requirement is, of course, to surpass standard quantum limit, and for that many groups try to implement a technique of spin quizzing using a cavity, or more recently there are some proposals to implement spin quizzing in free space. Sorry, and just to conclude, to go further in our group, our goal is to achieve this target. The first things what we want to do is to try to explain discrepancy with the cesium recoil measurement, and for that we are starting to do measurement with isotope 87 to check if there are some hidden systematic effect. And also we are building a new experimental setup where we plan to implement large momentum beam splitter, ultra cold atomic source, and for a long time spin squeezing if we are limited by SQL limit. Okay, thank you for your attention.
Thank you so much for a very nice talk. It was super interesting. I think we have some time, but maybe not too much for the question and discussion. So are there any questions? Or maybe I can ask you questions, because I was actually very interested to find that the limiting factor for sensitivity is actually the distortion on the wavefront.
Yeah.
So actually, I was thinking about maybe there's a nice way to improve it if you use some existing idea in the quantum information. So, for example, in the quantum information or qubit control, people sometimes use so-called composite pulse. So what it does is, if you want to apply, say, pi over 2 pulse of the pi pulse, instead of like directly applying pi or pi over 2 pulse, you make them as a multiple pulses, such a way that the imperfection in the pulse are automatically cancelled by one another.
No, it's not works. It not should works.
So
because
yeah.
But if I understand, the two pulses should be applied simultaneously. You mean?
No, like sequentially. But suppose you want to apply pi over 2 pulse, but
Yeah.
instead of doing that, you rotate to a different angle, but multiple times, and utilize the geometry so that it come back, so you achieve the same net effect, but the actual trajectory could be different. Such a way that you use a geometric property of this two-level system, so that so that you end up going to the same, implementing pi over 2 pulse.
Mm-hmm. No.
So I can give you one specific, maybe just stupid idea, but and the Fulgur is like shaking his head, so maybe maybe the stupid idea. Say, suppose you want to flip from 0 to pi. What you could do is you flip only pi over 2 and flip along, say, y-axis to rotate by 100 degrees, and then complete the pi over 2 later.
In fact, in our experiment, the effect of the distortion of the wavefront is during the coherent acceleration. You see, during the Bloch oscillation, not during the interferometer. Okay, because as we measure 1,000 record, okay, we enhance this. We are this effect that I mentioned is mainly present during the Bloch oscillation.
I see.
And during Bloch oscillation, we have we just apply a ramp frequency in order to transfer mineral to the atoms.
I see.
We don't apply P over 2.
Yeah, but even for during so it's a different idea now, but even for during this acceleration, can you utilize some theory of so-called counter-diabatic terms? So the idea is you do not like linearly ramp the frequency or linearly ramp the adiabatic sweep, but you do intentionally a little bit of time dependence one, optimize for a certain path, such a way that you achieve what you want to achieve.
Can I say something?
Yeah.
What we would have, the problem with the wavefront distortion is that the photon momentum is not omega over c.
C'est ça, yeah.
Because the beam, that holds only for plane wave. So whatever strategy we apply would have to overcome this error. If there was a way to invert the wavefront distortion, then sure, right?
Yeah. In fact, this effect is due to the fact that the K vector is not well defined. Okay, in this simple scheme that I give, when we have, if you have a plane wave, no problem, because the K vector equal exactly nu divided by c. But in this case, atom during the acceleration not seen the same K vector. There is dispersion between the K vector. And then we have to reduce this dispersion or evaluate it precisely, which is not easy. Because since you measure the profile of the laser of the wave front usually you measure it before sending it on the atom, and the atom are in the vacuum. And then since you choose a perfect optic, you distort this wavefront.
Mm-hmm. I see. So the absolute value of the wave function is important. Therefore, like this kind of composite pulse idea does not work. Is that the reason? Because we need to know the absolute value of it, and it's hard to tell if you have a variation.
You mean the wavelength? Or
yeah, wave vector. Yeah.
No, the wave vector, yeah, exactly, is really to determine, to be able to evaluate the wave vector seen by the atoms, the mean wave vector seen by the atoms. That is the problem.
Mm-hmm.
And as the profile, as I show, for example, if you have a local fluctuation of the intensity, these change the mean wave vector seen by the atoms during the Bloch process.
I would like to continue more, but maybe we'll also pause for other questions and some discussion points.
I think there was a question about the blinding process. I think Chris Pando was asking, so we can ask it for him. Was the experimental analysis blinded in some way, and if so, what was the procedure?
Yeah, in fact, when we did the experiment, as I mentioned, we measure the frequency of the Raman beam and also the frequency of the Bloch beam, because we needed to evaluate the value of H/M. And such measurements are done in an independent room using a frequency camp. And then we get data independently, and we analyze the data at the end. This is why our what we call our binding approach. We put a random value in the computer when we get data, and finally we determine the frequency of the Bloch and the Raman beams.
May I ask if the analysis of the systematic corrections are also blinded? Like,
No.
are you calculating them in several places and then you come together and assess from it what the disagreement is on these systematic errors? Because they seem to be really quite. I mean, it's an important correction in order to really place yourself in that fine resolution graph.
Yes, I agree with you. In fact, we had three approaches to evaluate systematic effect. By 3 and by 2, as I mentioned, we have a very good statistic. Then we can change some parameter to evaluate this effect experimentally. And in meantime, we do model and Monte Carlo simulation to check that these measurements agree with both modelization and Monte Carlo simulation. This is the way, and we have 3 approaches to test. And for systematic, that small systematic like refractive index due to the atomic cloud, we just evaluate such effect.
So let me just 1 second. So we often at this point have gone to like the session with students and postdocs, but we're also just kind of late into the hour. So I'm going to suggest that we just let the questions and discussion last all the way till 2 or as long as it lasts. And just for this last colloquium, not try to break up the discussion into 2 sessions. So Sunwon, keep asking questions and pull them out of the chat.
All right, great. So
Okay.
there's been a question, actually, like the same question multiple times. So essentially it's about the difference. So for the rubidium measurement, it seems like there's a slight difference in the disagreement between the old measurement and the new measurement. Could you comment on that? And that's one question. The second question is, it seems like there's also disagreement between rubidium measurement and cesium measurement. Could you comment on those discrepancies?
So I think the second question is also for Olga. So, but for the first, our previous and new measurement, we discover 3 new systematic effects that has not been taken into account on the previous measurement. For example, this effect due to the local fluctuation of laser intensity, which is a big effect, has not been considered in our previous measurement. Also, we have another effect due to the expansion of the atomic cloud, okay? Because during the the interferometer sequence, the atomic expand, and then the light shift observed by atoms at each p/2 pulse is not the same, and this has not been considered in this the previous measurement. And the third effect is the phase, electronic phase, that is observed on the phase lock loop. Okay, in the phase lock loop of the 2 Raman beam, we observe that there are phase shifts that depend on the sequence. And now we measure this phase shift and we correct it. That could explain, but unfortunately we don't have the ability, because the previous measurement has been done in another vacuum chamber with another vacuum chamber, and we don't have a possibility to check this. And for the second question, it's hard to give you the answer. We want to do measurement with 85 in order to check if there are some hidden systematic effect. But I think, in my opinion, for the Berkeley and Paris experiment, the main effect is due to this wavefront effect, and is really hard to measure perfectly the wavefront profile. Really experiment seen by the atoms. I don't know what you think about that, Olga, but in my opinion, the problem could come from this point.
Yeah, I agree with you on that. The wavefront distortion effect is the largest correction in both experiments. And so if I had to place a bet, I would say that's where to look for the reason. But in the end, physics is about having experiment and measurements. And until we have more data, it's hard to speculate.
Is there a theory model actually attempts to explain the difference between rubidium and cesium measurement?
There would have to be something stunning, like if all the measurements of the cesium or rubidium mass were off by many, many, many error bars, but it's very unlikely.
Mm-hmm. Mm-hmm. Yeah, there's another question. Let me just read it from the chat. Did you have a way of measuring the laser intensity inside the vacuum chamber after scattering from viewports and vacuum chamber walls?
No, when we in fact before doing the measurement, when we built the experimental chamber, we measure the profile by using Shackartman. Shackartman is device that measures the wavefronts of the laser. We in fact we did measurement with and without the optical windows, and we don't see big difference between the two. But in this configuration, we only use Shackartman, and we don't take care, to be honest, to the local fluctuation of the intensity. And the data, the correction to evaluate this effect has been done by measuring the profile of the laser intensity before the optical window. I don't know what Olga group did, but in our group we measure before the optical window. We don't have the possibility to measure the profile of the laser in the vacuum chamber.
Sorry, if I weigh in, I really like the trick that you employed, namely varying the intensity of the laser and see how the data varies with it.
Sorry? Okay.
Oh, we can talk about this later, but I said I like the trick that you use to vary the laser intensity,
Yeah.
and look how alpha varies with it. That gives some clues on what the laser beam looks like in the chamber.
Yeah, also there was a related question. It's about like what is the approximate size of the Gaussian beams used for the Bragg and black pulses? And also similarly, what are the approximate optical power required for your experiment?
For our experiment, optical power for the Bloch beam, we have 600 milliwatt per beam. Okay, and the waist is about 5 millimeter, the waist of the laser. Okay, and the Raman beam are about 400 milliwatt.
Yeah, I think it's very good to have this very active discussion here, but let's give a chance to non-experts. Like, is there any question from non-expert on the related experiment, but some other questions? Especially from ones like either theorists or like from a different field. Otherwise, let me bring that up. So like it seems like by the way, I'm very grateful that I learned about this, but it seems like the wavefront distortion is the like problem. But do you think it's a fundamental issue? Like at some point we can improve the technology to fix it, or maybe you can improve like software, like your pulse, like your interferometry, like interferometry scheme to be something else. And do you have any perspective? Like, do you think the technological improvement is essential to resolve those issues?
Yes, I think you can in the next version of the experiment we plan to use larger beam, okay, and also colder atomic source, okay, because and in this case can reduce this effect due to the Gaussian beam. As I mentioned, the effect of Gaussian beam scale on the 1 divided by the waist square of the laser. By increasing the waist of the laser, you can reduce this effect.
Yeah,
and
maybe
also,
a very stupid question, but from a totally different field, I was told that some people do this wavefront shaping by this DMD and then make like different type of potentials and so on. Like, is that technology very far from what you need?
So people try to use what to say SLM. SLM is adaptive optics to correct in real time this effect by the group of CIRC did that since years ago, but the conclusion not was positive. The adaptive optic not improve, reduce these effects. Voilà. And the discussing why with the group of CIRC to work on gravimetry, the promising way is really to use colder atomic source and larger waist. Of course, we also are working to study different optics that lead to flat laser profile. There are these, but these issues are technical issue, not fundamental issue, if you want.
I see. Yeah, we are almost like time is up. Maybe one is there, if there's any like question, maybe last question. If not, let's thanks the speaker again, and thank you so much for very nice talk.
Thank you. Merci.
Thank you so much, Saïda.
Ciao. Sorry. Thank you. Bye bye.